Hello world. So today we're presenting our project on reinforcement learning with AI agent. So first of all, what is reinforcement learning? Well, reinforcement learning is an area of machine learning in which agent is trying to find optimal policy or sequence of actions in a given environment to maximize its overall reward. Formulations of reinforcement learning problems are relatively old. However, with the advent of neural networks, this area got a new wave of excitement and research. One of the most important properties and equations in reinforcement learning is the Bellman equation. Bellman equation tries to answer the following question: what is the value of this state? So in other words, given the state I'm in, and assuming that I take the best possible action now and at each subsequent step, what would be the long-term reward that I can expect from this state? So this equation helps us to evaluate the expected reward relative to the advantage or disadvantage of each state. From the Bellman equation formula, we can see that we assign a value to each state, and we do that by taking a reward at this state plus the expected value of the other state given the action that we take following our policy, and we multiply that expected value by the discount factor. And this discount factor shows how much we value immediate reward or how much we value the future reward. A distinction should be made between reinforcement learning and other types of learning, such as supervised or unsupervised. So in the supervised learning setup, we initially have an input and output pairs. So we have a data and labels associated with it. However, in a reinforcement learning environment, we usually don't have any data, and we get this data while we interact with the environment. So we don't know in advance what the data we would have. Despite this, in certain environments, there could be similarities with supervised learning. As we can see in the following example, in the card pull problem, you can see the video here. The way we can transform this problem into a classification problem is by taking random actions in this environment and only taking records of the sequences of actions that are doing relatively well compared to the complete random actions. So for example, when doing complete random actions, we would on average get a reward of 11 points. However, we only take subsamples of those random actions where the average reward is about 50. The reason why we can do this is because we get continuous update of our reward from the environment. In other words, we always get a feedback from the environment on how well are we doing. So that's why we can turn this feedback into labels. Another thing to note is that our possible states and possible actions is relatively small. However, there is a greater number of situations where we cannot do that. And the reasons for that is because the sample space is quite large, and we cannot possibly get all the random actions, all the successful random actions from those samples, from that sample space. Also, in other situations where we don't have a constant feedback from the environment, we cannot do that also. So for example, in the following problem, we get a reward of +1 when we get our car to the top of the mountain. However, in other cases, we don't get any feedback from the environment. Here you can see the list of algorithms that we try to use in this problem. The first one I would like to talk about is Epsilon greedy Q-learning algorithm. On the following slide, you can see the pseudocode implementation for our Q-learning algorithm. I would not go into all the details of this code. However, one important thing about this algorithm is that we are updating the Q metrics at each step during the training. So in other words, we're training at every iteration during our training process. This is very different from a similar algorithm in which we train at each episode of the training. However, there are some problems with the naive approach. And the problem is when we're following our policy, we're not really exploring so much. So for example, if we're not taking a certain action, we wouldn't really know if this action was good or bad. We just simply never had a chance to take it. So that's why we're introducing the epsilon. So with the probability of epsilon, we would be taking a random action. And with the probability of 1 minus epsilon, we would be taking an action from our policy. Another idea is that this epsilon should probably decrease over time. And the intuitive idea is that at the beginning stages, where we should be taking more random actions because we really don't know much about our environment. However, as we making our learning progress, we should be more confident in our policy, and we should make less random decisions than before.
Hello everyone, so my name is Stefan, and I will be going over the DQN network. So DQN was first introduced in two of the paper playing Atari game in NIPS 2013. There are only a few papers about DQN between 2013 and 2015. We were guessing that this is probably due to the unstable training, and so that the researchers are not able to verify this, not able to reproduce the same result. So to verify this, our next algorithm is to do just the DQN without the fixed target. So even without a fixed target, we would still like our neural network to converge. So in order to do that, we place only a small neural network inside of our DQN. In this way, even though the goal is drifting, however, because the neural network itself is small, so it won't have the capacity to drift too far away. It will still try to generalize a little bit more. On the other hand, if we have placed in a much deeper and wider neural network, then it will have a capacity to drift very far away to try to fit different kind of goal, and this is really not what we want. So looking at the first video, this is a video where the agent is very struggling within the valley, and this is due to the low gamma that we have set it. This gamma is set between 0.8 to 0.9. We want to test it out how much the gamma actually affect the agent. So on to the next video, the gamma is actually set high. This is set to 1. So you can see that even though the agent is still struggling, but overall it's performing much better than the previous agent. Now on to the twist for our neural network, which is we have introduced a reward modified reward function based on domain knowledge. So as a programmer, I actually actively induce some bias into the reward function in hope that the agent will be able to learn much better. So looking at the first equation, I modify the reward function such that the reward is multiplied by the inverse of absolute value of the position the agent is in, as well as multiply that by the inverse of the position, the velocity of the agent. So intuitively, if the agent is able to get a higher position, then it shouldn't be penalized as much because getting a high position is actually part of what we want. And on the other factor as well, if the agent is able to get a faster velocity, then this is also what we want. So the agent should be penalized less instead of everywhere it goes, it gets a -1 result, reward. So looking at the first video, this is the modification we made, and this is our result. So even though the agent is doing okay, but it's still not doing well enough. And we suspect is that the reward is actually drifting a lot because the reward now is like multiplied by 2 of the multiplier. So in a sense, the agent will have a harder time to learn the reward because the reward is somewhat more chaotic now instead of just a -1 constant. So to improve on this, we kind of step back and then do a less greedy algorithm, do a less greedy modification on the reward function. So now onto the second equation, it's pretty much the same as the first, except that we take out one of the multiplier, the position. Right now we only leave in the velocity. And to our surprise, this actually helped the agent converge much faster. So looking at the video, it really does extremely better than the previous video agents. On average, I would say it probably converged two times or more on the convergence rate compared to all the other agents. This kind of makes sense because whenever the agents see that, oh, it is getting less penalty because it's going at higher speed, it will try to do that more. This concludes our twist as well as our modification on the DQN.
Another closely related problem that we explored as a part of our project was a continuous state space mountain car problem. So as we approached the continuous state space mountain car problem, we encountered a large state space. So instead of using Q-learning, which needs a representation of each state's values, we tried something else. While the goal of Q-learning is to approximate the Q function and use it to infer the optimal policy, policy gradients is a method that seeks to directly optimize in the policy space. What do we mean by that? In policy gradients, we usually use a neural network or other function approximator to directly model the action probabilities. Each time the agent interacts with the environment, we tweak the parameters of the neural network so that good actions get sampled more likely in the future. We repeat this process until the policy network converges to the optimal policy. This helps especially for continuous state problems, as policy spaces are usually smaller than state value spaces. Formally, the objective of policy gradients is to maximize the total future expected rewards, which are represented by the sum of future discounted rewards. We want to iteratively tweak the parameters of our policy network so that the total future expected rewards are maximized. How can we achieve that? This is where policy gradient comes in. It turns out that there is a nice formula for the gradient of total future expected rewards, which allows us to use gradient descent to maximize total expected future rewards by minimizing the loss function. When we applied this algorithm to our problem, we found that our algorithm began to learn quickly, but ultimately found itself stuck in a local minima, unable to improve as the reward got closer and closer to zero. So we need something better. So far, we've seen value-based methods where we estimate the value functions, and the policy is usually implicit, such as epsilon greedy or stochastic exploration, as we've seen. We saw policy-based methods just now, where we estimate the policy, but there is no value function. Let's now see a hybrid called active critic methods, which will estimate the policy and estimate the value function. The policy used to generate the samples could be different from the one which is evaluated and improved, i.e. the behavior policy of a model may be different from the target policy. This allows the critic to learn about the actions which are not preferred by the target policy and therefore improve the target policy. In the policy gradient method, we had another big problem. We are in a situation of Monte Carlo, waiting until the end of episode to calculate the reward. We may conclude that if we have a high reward, all actions that we took were uniformly or average good, even if some of them were really bad. What if, instead, we can do an update at each time step of our policy gradient method? The active critic model is a better score function. Instead of waiting until the end of episode, as we do in the Monte Carlo version of policy gradient method, known as reinforce, we make an update at each step. This is also called temporal difference learning. Because we do an update at each step, we can't use the total rewards instead. Instead, we need to train a critic model that approximates the value function. Remember that value function calculates what is the maximum expected future reward given a state and an action. This value function replaces the reward function in a policy gradient that calculates the reward only once at the end of the episode. We implemented an active critic method on our algorithm, and the results look good. We got some convergences pretty earlier on. However, we found that the variance in our results are quite large. Here's a quick chart comparing policy gradients to active critics. So you see what I mean. While policy gradients got stuck at the minima, active critics made progress. But the variance is still large. This is not so desirable as it's happening largely because our updates are based on individual actions updates. An action may be bad, but it might still be the best available action in that particular state. We can get around this problem by updating on the basis of the action's reward in the context of the state's value. That is, by updating as per the advantage or the disadvantage that action carries in the current context. By subtracting a proper baseline, such as the state's value, we ensure that the scaling factor is only positive if the action is good and negative if the action is bad compared to that baseline. Empirically, this trick will reduce variance of the gradient estimate quite drastically. Implementing this algorithm yielded the most consistent convergences on a continuous mountain car problem. Here's a quick chart showing the kind of advantage critic methods have over traditional active critic models. And this is it for this video. We enjoyed doing this project thoroughly, and we hope that you enjoyed this video in which we covered methods such as Q-learning, deep Q networks, policy gradients, and ultimately advantage critic models. We applied these algorithms to two different kinds of problems, or variants of the same problem, the mountain car problem, one that is discrete and the other which is continuous. In the course of this project, we found some methods which we haven't covered in this video, such as neat neuroevolution of augmenting topologies, which we found were working even better than some of the methods that we have discussed in this video on these problems. We hope you enjoyed it. Thank you.